Hello. I'd like to talk with you today about antiderivatives in the realm of indefinite integration. So in the world of indefinite integration, we seek to answer the question, what is the integral of f of x dx? What we want to be able to do is write down what the function is that answers this question. We'll say f of x equals the integral of f of x dx, if in fact f is an antiderivative. So when I write down this statement right here, what I'm saying is that capital F is an antiderivative of lowercase f of x. And the symbology of making the antiderivative be capital and the integrand be lowercase seems to be rather canonical throughout the calculus literature at this point. So it seems like a pretty good convention to take that when I integrate or antidifferentiate, my letters go to capital letters, because that seems really useful. Okay, so I just wrote down a thing here. I said that f is an antiderivative, and I think it's important that I stress that there is an infinite number of antiderivatives of f. But first, I think I should explain what do we mean when we say antiderivative, because I haven't quite said what the relationship is yet. I mean, I kind of did. I kind of said the relationship in the sense that capital F is the integral of lowercase f. But what I really mean, I get to write this down if I get to call it an antiderivative if d capital F dx is equal to f of x. So when I take the derivative of capital F, do I get my integrand back? And if so, then I get to call capital F an antiderivative. So why antiderivative? Well, because if capital F is an antiderivative of lowercase f, then capital F prime is equal to f, but so is capital F prime, so is capital F plus 5 prime equals lowercase f. Why? Because this thing is equal to capital F prime plus 5 prime, but the derivative of every constant is just 0, so that's just capital F prime, which we already established is lowercase f. And there was really nothing special about the number 5. I could have written pi. I could have written a billion. I could have written some symbolic constant, which is exactly what I'm going to do right now. I could write down c, and I see that if I have an antiderivative, I can get any other antiderivative simply by making an additive constant onto my function. That is to say that the antiderivatives for a function have some like basic form in terms of capital F, and then everything else is just an additive constant away from it. So when I integrate, this is kind of the point of this in some sense. So when I integrate, when I do something like the integral of 5x squared plus 5x minus 1 dx, I'm going to get something right back here, and then I'm always going to be like plus c, because that's this constant of integration, because this is the thing that really says together that I have the general antiderivative of this thing. And so it captures that an infinite family of antiderivatives by putting plus c on the end there. As a kind of a coda to that story, as I wrap up, if I wanted to find the c, then I would say that c comes from initial conditions. or some other related way of picking out what that particular value of c is. So that's antiderivatives. Antiderivatives are functions where I can take the derivative and get my original function back, get the integrand back, and they're all an additive constant away from each other, which is why when I do indefinite integration, I need to put my plus c's on the end to have the fully generic answer for what the antiderivative is. Thank you so much, and I wish you all the best.